Welcome back to geometry. In this video we're going to do 13-2, the sine and cosine ratios. This section will take a couple of days. So here in the warm-up we've got Emily looking at a flagpole that is 25 feet tall. From where she's standing, the angle made between the ground and the top of the pole is 40 degrees. How far away from the flagpole is Emily? Well, we've got the opposite side and we want the adjacent side. So this sounds like a job for tangent. The tangent of 40 degrees equals opposite 25 over adjacent CB. If we multiply both sides by CB, it's now over here. And then we're going to divide through by the tan of 40. So the side length of CB is 25 divided by the tan of 40 degrees. If pushing the buttons on the calculator goes well, you should find that she is about 29.8 feet away from the flagpole. Okay, and number 2, label the sides of the triangle as opposite, adjacent, or hypotenuse in relation to x. Now it doesn't matter what angle we're looking at, the hypotenuse is always across from the right angle. So this is the hypotenuse. Now we're down here at angle x. The side that is across the triangle, not touching angle x, is the opposite side. And then here in angle x, one of the sides that make angle x is this adjacent side. Okay, now to get started here, we've got this little activity. We've already seen that the tan function is equal to the opposite side over the adjacent side. In this lesson, we're going to look at the sine and cos ratios. So once again, we're going to be making fractions out of the sides of a triangle. So I got two triangles here. I measured and labeled their side lengths. Measure each side, label the figures. Did it. Measure each angle. Explain why the triangles are similar. Well, angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. I only need two of these, and I could say angle-angle triangle similarity theorem. Okay, let's make some ratios. So it says calculate the ratio of the leg opposite A to the hypotenuse. So here I am at A. The opposite side is 1.9. That's our numerator. Our denominator is the hypotenuse, 2.8. So 1.9 over 2.8. And now here we're going to do the same thing from angle D in the other triangle. The leg opposite over the hypotenuse. So here we are at D. Opposite is 2.9 over hypotenuse 4.3. Now I see here it does say round to the nearest tenth. So I've got my calculator. I'm going to do that first one, 1.9 divided by 2.8. That would be about 0.7. And then the other one, 2.9 divided by 4.3 is about 0.67, or again, about 0.7. They are the same. What should be the comparison between the ratios? Well, they should be the same. They did come from similar triangles, so they will have the same ratios. Okay, now we did that angles A and D. Or we did the opposite side and the hypotenuse. Opposite side and hypotenuse. Let's do the same thing now with the adjacent side and the hypotenuse. So back to the first triangle. Here we are at angle A. The adjacent side is 2.1. The hypotenuse is still 2.8. So this will be 2.1 over 2.8. And that divides out to be 0.75, or we can round it off to 0.8. Same thing on the bigger triangle. Here we are at D. Adjacent side is 3.2. over 4.3. So 3.2 over 4.3. Beep, beep goes the calculator, and I get 0.74. You know, the other one up here was 0.75. This one is 0.74. So I don't want to round it just to 1/10, or we might be way off. So what should be the comparison between the ratios? Again, they are the same. Now, part E, do you think the same results would apply in any similar right triangles? Well, as long as they're similar, yes, the same results would apply. Why or why not? Well, we saw, especially when we were doing the last lesson on the tangent ratio, ratios of corresponding sides on similar triangles, on similar right triangles, are equal. Okay, is that the end of the activity? Yes. All right, so now we're going to see what we just found, the sine and the cosine of an angle. So the ratios we calculated in that example are called the sine, S-I-N-E, and cosine, C-O-S-I-N-E. These will be abbreviated S-I-N and C-O-S. So the sine ratio, the sine of angle A, is the length of the side opposite angle A divided by the length of the hypotenuse. The cosine of angle A is the length of the side adjacent to angle A, and the length divided by the length of the hypotenuse. So now you have three trig functions to memorize: the sine, the cosine, and the tangent. Now here's a little mnemonic trick. So, ka, toa. Or I prefer to write it like this: S-O-H I could write as S-O-H. C-A-H will be C-A-H. T-O-A, T-O-A. The sine of an angle is the opposite side over the hypotenuse. The cos of an angle is the adjacent side over the hypotenuse. The tangent of the angle is the opposite side over the adjacent. So all over the internet there are mnemonics to help memorize these. I'll still never forget the one I learned in high school. Some old hippie came a-hoppin' through our apartment. So in example 2, find the sine and the cos of angle A. So here we are at angle A. The sine of angle A is equal to the opposite side, 18, over the hypotenuse, 30. We could reduce that fraction down to 3/5, or as a decimal, 0.6. The cos of angle A equals the adjacent side divided by the hypotenuse. That would reduce down to 4/5, and that as a decimal would be 0.8. All right. In example 3, find the sine and the cos of angle B. Angle B is up here. Now notice our triangle is missing a side. So probably the first thing we should do is the Pythagorean theorem to find that missing side CA. Hypotenuse is 18. So our Pythagorean theorem will be 10 squared plus AC squared equals 18 squared. So that'll be 100 plus AC squared equals 324. We'll subtract a hundo from each side. AC is 2, or AC squared is 224. And we take the square root, and we're going to get about 15. 14 point something real close. So we'll just call it 15. Now, the sine of angle B. So we're up here at angle B. Sine is opposite over hypotenuse, 15 over 8. that fraction reduces to 5/6, or as a decimal, approximately 0.88 repeating. The cos of angle B, again, we're back up here at angle B, the cos will be the adjacent side over the hypotenuse. 10/18, that'll reduce down to 5/9, or as a decimal, about 0.55 repeating. Okay, easy enough. All right, here in example 4, we've got a pretty nice picture, suspension bridge. We've got a bunch of little triangles in there, and it says in triangles DEF. So here, I'll hit in red, is DEF. And then we've got CEG. So CE will be this blue side, and then the G will take us up to here. So it looks like DC. Yeah. Calculate the sine and cosine for angles DF, C, and G. All right. So sine of D, let's see. I'm going to do my fractions up here, and I'll put my decimals underneath the picture. So here we are at angle D. I'll hit it in red ink. Sine is opposite over hypotenuse. The opposite side will be FE, and FE is 2.5. And we're going to divide that by the hypotenuse here, 6.5. So if we divide 2.5 by 6.5, we get approximately 0.385. So that is the sine at angle D. Let's do the cos at angle D. So cos would be this adjacent side. This side goes from 18 to 24, so that is length 6. And we're going to divide that by the hypotenuse, 6.5. And that is approximately 0.923. Okay, I'm going to switch to blue ink, and we're going to move to angle F. Angle F is in the same triangle, but it's up here at the top. So the sine of F, sine will be opposite, that side is 6, over hypotenuse, 6.5. 6 over 6.5, we kind of saw that already. That's going to divide out to 0.923, approximately. Now, back again up at angle F, cos will be adjacent over hypotenuse. That'll be 2.5 over 6.5, and that divides out to 0.385. Look at this. The sine of angle D is exactly the same as cos of F. And the sine of F is exactly the same as the cos of D. What do we know about angles D and F? Well, in a right triangle, we got 90 degrees here, angle D is here, angle F is here. These have to add up to 90, so they're complements. So something is going on here with these complement angles and their sines and their cosines. Okay, let's move up to a bigger triangle. Now we're looking for sine of C and cos of C. C is right here. The hypotenuse of C is 13. And then we've got this side GE. GE is length 5. So if I'm down here at angle C, sine is opposite over hypotenuse, 5 over 13. And 5 divided by 13 is about, 0.385. Look at that. Cos of angle C. Again, we're back here at C. Cos will be adjacent over hypotenuse. In this case, that'll be 12 over 13. 12 over 13 divides out to approximately 0.923. Look at that. Okay, now I'm going to switch to red ink. We're up here at the top of the triangle at angle G. And the sine of G is opposite over hypotenuse. 12 over 13 divides out to be 0.923. Again, back up at G, we're going to find the cos. That'll be the adjacent side, 5 over the hypotenuse, 13. And then that turns into the decimal 0.385. So again, lots of 385s, 4 of them, and everything else is 0.923. Again, these are ratios in similar triangles, so they do have that built-in relationship. All right, now I think we got some questions here on the next slide. Why are the triangles similar? What do you notice about the sines and the cosines in the similar triangles? So the triangles are similar by angle, triangle similarity theorem. You know, they all have a right angle, and then we have our angles here on the bridge. What do you notice about the sines and the cosines in the similar triangles? They all equal the same two values. They equal the same two values. So then part C, what relationship exists between the sine and the cosine ratios of a pair of complementary angles in a right triangle? Well, we could say the sine of one angle is the cos of the other angle. And vice versa. And vice versa. So we could switch them. And again, we saw that numerically here. What was it? D and F were in the same triangle. So in triangles D and F, we only got these two values. The sine of one is the cos of the other. The sine of F is the cos of D. Oops. Is the relationship true for any pair of acute angles in a right triangle? Yes. And then for explain, we could just say something like one angle's opposite side is the other angle's adjacent side, is the other angle's adjacent side. Okay, what's next? Boom, a little calculator work. So just like we did with tangent on our basic TI-30s, for the sine of 30, I would type in the 30, and then I would hit the sine key. I would make sure I'm in degree mode, and I would get 0.5. Sine of 30. Sine of 15, 1.5, hit the sine key. We're going to get about 0.259. Next, cos of 60. Cos of 60 is also 0.5. So here we have a sine and a cos. The angles are complement angles. These add up to 90 degrees. So their outputs will be exactly the same. Last one, cos of 110 degrees is approximately negative 0.342. Okay, I believe that's the last example. Oh, no. Oh, yeah, the last example. Team huddle. You know, here's some work for you to try on your own. I encourage you to pause the video, try the problems, and then fire the video back up. See if you got them right. Did you pause the video? Are you sure? Fill in the blanks. The sine ratio compares the lengths of the opposite side to the length of the hypotenuse. Cos compares the length of the adjacent side to the hypotenuse. Just never forget, some old hippie came a-hoppin' through our apartment. Now this little thing here, that's I believe the Greek letter alpha. It's going to represent our angle like theta or any other variable. So it says find the sine and cos of alpha, write each as a fraction and as a decimal rounded out to 4 places. So the sine of alpha, SOH, some old hippie, opposite side over hypotenuse, that'll be 8/17. And we would divide that out and get approximately 0.4706. Now again, we're still at angle alpha here. Cos is adjacent over hypotenuse. So cos of alpha is 15/17, which is approximately 0.8824. Find the sine of angle S, the cos of angle S. Write each answer as a fraction and decimal. So the first thing we got to do is figure out SR. Note that SR is the hypotenuse, so that'll be our C value. So we're going to have 16 squared plus 30 squared equals, I'm going to H for hypotenuse squared. So that's 256 plus 900 equals H squared. That adds up to 1156, and we're going to take the square root of that to find H, and that turns out to be 34. So I'm going to write it up here on my triangle 34. And now we can find the sine and the cos of S. The sine of angle S, here's angle S. Sine is opposite over hypotenuse, 30 over 34. That would reduce down to 15 over 17, or approximately 0.882. The cos from angle S, here again we are at angle S, cos is adjacent over hypotenuse. So that'll be 16 over 34. That'll reduce down to 8 over 17, or as a decimal, about 0.471. Okay, in number 4 here, we've got some triangles here on the graph paper. Notice we have the hypotenuse filled in. LM looks like it's 3 boxes. MN is 4 boxes. And we've got a 3, 4, 5 triangle. And then in the smaller one here, side GH is 2. And it looks like the other side there we'll say is 1.5. So let's see, first here in part A, sine of G. So we're up here at this angle at the top of the smaller triangle, and from angle G's perspective, the sine would be opposite 1.5 over hypotenuse 2.5. And that divides out to a nice 0.6. The cos of G would be the adjacent 2 over the 2.5, and that comes out to 0.8. So sine is 0.6, cos is 0.8. Sine 0.6, cos 0.8. Now let's go down to part B. Now we're going to go to angle L. That's right here in the bigger triangle. So the sine of angle L will be opposite 4 over hypotenuse 5. 4/5, and that as a decimal would be 0.8. The cos at angle L would be the adjacent side 3 over 5, and that divides out to 0.6. I recognize those decimals from part A. So again, to recap here, the sine of L was 0.8. The cos of L was 0.6. Okay, now we're going to move to a different angles again. Sine of I and the cos of I. So now we're down here on the blue triangle in that lower right corner. Sine of I will be opposite. Sine of I is opposite 2 over hypotenuse 2.5, and that comes out to 0.8. The cos of angle I is going to be adjacent 1.5 over 2.5, and that divides out to a 0.6. And now our last angle, angle N, that's down here in the bigger triangle. The sine of N is opposite 3 over hypotenuse 5, and that comes out to be 0.6. And the cos of N is going to be the adjacent side 4 over hypotenuse 5, and that's 0.8. So now that we've done all that work and got all these decimals in the figure, how could we prove that the triangles are similar? Well, we could do angle and stuff, but now, you know, the angles are sort of built in here into these sines and cosines. So the sine and cosine ratios, the sine cos ratios are the same for the pairs of acute angles, are the same for the pair of acute angles. What is the trig relationship between the complement angles within each triangle? The sine of one angle is the cos of the other angle. And remember, these are complement pairs. So the sine of one angle is the cos of its complement. Oh, and that's the end of the huddle, and that's the end of the video. I hope it was helpful.